Up everybody? Another snow day. I just didn't feel like we could wait around until we get good weather, so I made a little video of notes to try and get a little progress kind of going on where we're at. So I'm still in this packet that we handed out in class. Last place we were at, where we left off, is we did that activity where you guys created a sampling distribution. We played around with those pennies. I made you create a sample, find a statistic about that sample, and plot it up on the board. And if you remember, some of our distributions were approximately normal, and some of our distributions definitely were not. So what we're going to look into now is why do some of those distributions end up being approximately normal, get that nice bell curve, and why do some not do that? So what you may need to do is pause the video and write down these notes for the top of the next page. So feel free to pause me. I have everything on the page, and then I'm going to talk through it, okay? So if you haven't done so already, pause me and then unpause me once you have everything written down. So there are three, you might hear me use them interchangeably, assumptions or conditions, that if these three things fall into place whenever we are collecting our samples, we know things are going to end up being approximately normal, which just opens up so many possibilities for us. So my three conditions / assumptions are randomization, 10%, and then the third one, I call it the large counts kind of thing. So we're going to be focused on specifically proportions in this packet. Proportions, we'll do means in our next packet. So we're looking at, if I get a sample of like 36, how many out of 36 meet the criteria we're doing? So what we were doing with the pennies was we collected a sample of pennies, and I wanted to count up and get a proportion of pennies that had a year on them of 1992 or more current or bigger than 1992. So proportions. So the three assumptions are randomization. We want to make sure the sample was randomly selected. So I'm going to talk about what they are over here and then their purpose behind them in red ink over there. So the first thing that you have to make sure is when you're selecting your sample, it has to be randomly selected. The second thing we do, and I just keep it simple, I call it the 10% condition here. You want to make sure your sample cannot be more than 10% of the population, okay? So if we have a massive population, we want to make sure our sample is smaller than 10% of that entire population. A lot of times I'll just state that this is happening, but you can check by take your sample, whatever your sample size is, that's small, lowercase n here, and multiply it by 10. If you take your sample size, multiply it by 10, and you're still smaller than the population size, you've met the 10% condition, okay? So we want to make sure that. The third thing is large counts. What we're going to do is we're going to do n times p and make sure that's greater than or equal to 10, and n times q and make sure that's greater than or equal to 10. So here, n is our sample size. We're going to take our sample size and multiply it by p. P is our population proportion. So n times p, make sure that number is greater than or equal to 10, and then take n times q. Q is like the anti-p. Q is like 1 minus p. So if p is 25% or 0.25, q is going to be 75% or 0.75. So np and nq both need to be greater than or equal to 10. Now here's kind of the individual purpose of these, and we'll talk about how all these are playing together. So these top two, in a lot of textbooks, a lot of people bundle these top two together because they are ensuring together independence, making sure an individual data point in my sample is independent of another. There's no kind of influence, there's no play on there. So individually, the randomization is going to make sure we can generalize, once we really get into this, generalize any results or conclusions that we find to the entire population, okay? So we like that random selection. The second one is showing, a lot of times we're going to be doing sampling without replacement. Showing that, the fact that you collected a sample of each, individual thing without replacement is okay. But together, these the randomization and 10% are ensuring independence, which is a good thing. Our third assumption is a big one. This is making sure our sample is large enough, and it's going to make sure our sampling distribution is approximately normal. So you might have had me show you in class, why did some of our sampling distributions end up looking nice and pretty and get that nice, pretty bell curve? And then why did some just look like an absolute train wreck? Mostly what I was violating is I was violating this third assumption. The ones that end up nice and pretty, we get a sample that is large enough. We're going to get that sampling distribution that looks approximately normal, get that approximate bell curve. Whenever I had sampling distributions in the poster on my board that was all messed up, that's because our sample was just way too small. That's how we got that to happen. So when you violate this, your sampling distribution kind of goes to garbage. Okay. So if all of these things happen, when we're doing these problems about sampling distributions, the first place we go is we make sure those assumptions are all there. Boom, 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 randomization 10%, and then the large counts. If we get all three assumptions and we can verify, yes, these are happening, we know the shape of our sampling distribution is approximately normal, okay? And this is what opens up doors and allows us to do other statistical things. So every problem starts with the assumptions. We always, always, always start here because that's just kind of verifying, can I do this problem? Can I even go anywhere with this? Or I'm getting, some sort of graph that is not like this. It's all jacked up. If it's all jacked up, nothing's going to make sense to it. You can't do anything. So we start with our assumptions. We say, hey, we're all set. I know this sampling distribution because of the assumptions. I know it's approximately normal. And what we have found in statistics that is, if your sampling distribution is approximately normal, and we're going to specifically look at sampling distribution of proportions, we know a few facts about the center of that distribution and the spread. So if you could think to the activity we did, where you guys put those dot stickers, and we made distributions on up on my boards, we can now find the center of those distributions, and we can find the standard deviation of those distributions as well. And that just opens up so much for us. So what we know is if you want to find the average or the mean of this sampling distribution of sample proportions. So I have mu with a subscript p hat. So this is saying, yes, this is a mean. It is an average, but it's an average of all of my p hats. It's an average of all those dots that we have up on the board. And what statistics says is if you want to find the average of all of those dots that you guys put on my board for proportions, it is just p. The center of all of those dots should be non-biased and lined up to my population proportion p. And what we also know is if I take the standard deviation of all those dots, so the standard deviation of all those p hats, we know the standard deviation is just p times 1 minus p divided by n, and we're going to take the square root of that, okay? If you want to pause me and write those down, these are what we know about my sampling distribution. So it's kind of there really is a very routine order to these problems that we say, all right, I got my assumptions. We're all good to go. Now I got, yes, the shape of my sampling distribution is approximately normal. And once I know it's approximately normal, then it leads you to say, okay, well, what do you know about this sampling distribution? And that's how you find, the center is at p. The standard deviation is the square root of p times essentially q divided by n. Once you have that, man, so many possibilities open up for us. We can do a lot of things, and some of you might be able to see where this is going. So I'm going to do, I'm supposed to keep these notes brief on snow days. I'm going to do, on the example page, I'm going to do the first problem, start the second problem, but I'm not going to finish it. I think I want to leave the conclusion for the second problem for when we're back in person to make sure this is all tidied up. So I want to go through these two problems, and that'll be the end of this video. So first example, the FDA reports that 72% of Americans have a favorable view of eating at Taco Bell and think it is delicious. Suppose for your school project, you wanted to take a random sample of 150 Americans and you found 114 have a very favorable view of Taco Bell. Okay. So there's a little bits of information in here that I think is important to point out. First off, we are given a proportion here. Okay. We are given a proportion 72%, which I like to represent my proportions as decimals. So instead of 72%, let's call it 0.72. This proportion is of all Americans. So the FDA reporting is every single American, 72% have a favorable view of eating at Taco Bell. That means I got a population P, a population proportion P. So I know my population P is equal to 0.72. That's a good thing to pick out. Other things I see as we keep reading on, we're taking a sample of 150. So I got lowercase n. I got a sample of 150 Americans and found out of my sample of 150, I found 114 have a favorable view of Taco Bell. So what we have there is we have a sample proportion, which we represent as P hat. So what we had is we had 114 out of 150. 114 over 150, which for that math, it is 0.76. So I just pull out relevant information and label it from the get-go, okay? If we keep reading, it says, if we were going to construct a sampling distribution of all samples of 150 Americans, what would the shape of the sampling distribution be, and what does the mean in the standard deviation, okay? Now, before we can say anything about our sampling distribution, whether, hey, what's the mean, what's the shape, all those things, we need to make sure first, are all of our assumptions met, okay? Are all of the things that we're asking for, are they met, okay? So that was the first three things you wrote down today. So the first thing I'm going to check is, do we have randomization? So when I read through this problem, you kind of skim through it pretty quick. It does say we took a random sample. So all I'm going to say for random is I'm going to say our sample was randomly selected. Check. Great. Grand. Wonderful. Okay. The next thing I'm going to check is our 10% assumption there. Our 10% assumption. So that's making sure my sample is not more than 10% of the population. So back when I was talking about this, what we can do is you can take your sample size, which is 150, and multiply it by 10. Take your 150 and multiply it by 10. And if you do that, I get 1,500. So how you check it is you got to ask yourself is, do I believe my population is bigger than 1,500 people? Well, since we're talking about Americans as my population, yes, I do believe there's more than 1,500 Americans in my population. So what I'm going to say is my sample is not larger than 10% of the population, okay? My sample is not bigger than 10% of the population. And then the final assumption we check is our large counts. Now, this is the one that is going to change depending on what type of problem we're doing. Since we're dealing with proportions, it's going to be one thing. Once we start doing means, you're going to see this changes a little bit. So what we need to check is NP is greater than or equal to 10, and NQ is greater than or equal to 10, okay? So what I'm checking is if I take my N, which is 150, my N is 150, and multiply it by my P, which is 0.72. 150 times 0.72, and I'm a little bit kind of low on my calculators in front of me. 150 times 0.72. I don't have it exactly in front of me, but I'm going to tell you right now, I guarantee that's greater than or equal to 10. So you just need to, you don't need to, you can calculate it, quick check. That is greater than or equal to 10, good to go. But it's not okay just to check NP. You have to check NQ as well. So I'm going to do 150 times Q. Well, if 0.72 is P, then 0.28 is Q. It's like the anti-P. 150 times 0.28, that number is also going to be greater than or equal to 10. So we have our randomization, we have our 10%, and we have our large counts assumptions all good to go. So when these assumptions are all met, what we now know is we now know about the shape of the sampling distribution. We know the shape of the sampling distribution. So what I know is the sampling distribution is approximately normal. We're going to get that nice bell curve shape there, which is going to open up a lot for us. It's very logical steps here, okay? Very logical. That's why I'm number 1, 2, 3. So our assumptions are met. Therefore, I know things are approximately normal. And then now that gets us to the actual question here, which says, hey, what is the shape? Got it. And what is the mean and standard deviation? The mean and standard deviation, I can now do those. So what I know is the mean of all these sample proportions. The mean of all these sample proportions. So mu with a subscript of p hat. The average of all of those p hats is just going to be p, is what we wrote down on the last page. So the center of this is at 0.72. The center of this is at 0.72. And then I can also find the standard deviation of all these p hats. A little bit more complicated calculation, but it is going to be p times 1 minus p divided by n. So that is 0.72 times 1 minus p, 0.28. 0.72 times 0.28, and divide by my sample size, 150, and then take the square root of that. I'm peeking at notes from last year to know this calculation. I left my calculator at school. 0.0366 is that standard deviation. Okay, so with this information, follow the assumptions, get your shape, get your mean standard deviation. You're good to go. I'm going to start number 2, and then I'll be done with our notes for today. And we'll pick this up next time we're back at school. I'm going to start number 2. Let's get it. The CDC reports that 22% of 18-year-old women in the U.S. have a body mass index of 25 or more. As part of a health check at a large college, the physical education department requires students to come in and be measured and weighed. This year, the department decided to try out a self-report system. It asked 200 randomly selected female students to report their heights and weights. Okay, so before I get into the second piece here, part A, let's pull out relevant information. I had a proportion, a 22% that showed up here. That is the all 18-year-old women in the U.S. So that is a population proportion. That is P equals 0.22. P equals 0.22. Another number that showed up, there's this 25. That's just has nothing to do really with the stats. It's just like what qualifies you to be in our proportion. But it's not anything statistically weighted. It's not our sample size. It's not our P, or it's not our P hat. But there is this mention of, hey, they got a 200 randomly selected female students. That is your sample size. Your sample size is 200 there. So if we did multiple samples and constructed a sampling distribution of sample proportions of size 200, what is the shape and what would be the mean and standard deviation of the distribution? So I'm going to go through the same 3 things. I have to start with my assumptions to make sure is the setup of this sampling distribution actually what we think it is. And then once I check my sampling distribution assumptions, then I could talk about the shape, and then finally I could get my mean and standard deviation. So I'll move a little bit quicker through these 3 because I know this video is running on long. The first assumption is randomization. So we need to go back and check the problem and see, was my sample randomly selected? Which if you check right there, 200 randomly selected females. So I'm going to say sample, we'll say sample of 200 was randomly selected. Sample of 200 was randomly selected. Good to go. My second assumption is the 10%, the 10% check here. Okay, making sure our sample is not too big. Well, if you take our sample of 200 and multiply it by 10, 200 times 10 is 2,000. So you got to ask yourself, do you believe there's more than 2,000 18-year-old women in the United States? Yeah, I'm gonna go ahead and safely assume there's more than 2,000 18-year-old women in the United States. So sample is less than 10% of population. Sample is less than 10% of population. Our final check is the large counts check. So we got to check NP and NQ. NP and NQ. So if we're checking NP is greater than or equal to 10, we're taking 200 times 0.22. 200 times 0.22, which that would be 44. That's definitely greater than or equal to 10. And then we got to check NQ is greater than or equal to 10. So we're taking 200 times, what would that be? 0.78. 200 times 0.78. What is that there? Is that 156, I think? 156. That's greater than or equal to 10 as well. So randomization met. 10% met. Large counts met. So what we know is the sampling distribution is approximately normal. We know our sampling distribution is approximately normal. From there, we can finally get to what this question was asking us for, which is, hey, what is the mean and the standard deviation of all this? So if you want to find the mean of all of those sample proportions, if you want to find the mean of all of those p-hats, it is just p, which is 0.22. It is just p, which is 0.22. If you want to find the standard deviation of all of those sample proportions, well, that is a little bit more complicated. P times 1 minus p divided by n. So that is a 0.22 times a 0.78 divided by 200. And then we're going to take the square root of it. Again, I'm using old notes here. It looks like I had a 0.029 as my calculation. That is sampling distribution stuff. It's a little bit of writing, but it should be easy writing. Just very logical stuff. Am I allowed to do the problem? Okay. Since I'm allowed to do things, what does the problem look like? What do we know? And then you're going to see, all right, now that I have a mean and a standard deviation and things are normal, what could I do with that? And that's where I want to pick up, hopefully, whenever we're back to school and we have class again. Again, you need to pause this video, rewind it, get all the notes you need out of it, and you'll be good to go.